Hello everyone. Welcome to my stream. I'm just going to be hanging out and chatting. I'm going to wait for people to come in to chat if they do. Though usually I don't see anyone in chat during a stream. Though usually I don't see anyone in chat during a stream. Though usually I don't see anyone in chat during a stream. Wait. Though usually I don't see anyone in chat during a stream. Wait. Though usually I don't see anyone in chat. Okay, sorry about that. I forgot to mute my stream. Anyway, did you hear about the new LK99 thing? We're able to get superconducting metals at room temperature now. No need for liquid nitrogen, helium, etc. I'll try to see if I can find some articles on it.
LK99, excitement rises over possibly revolutionary miracle material, but there is still no good reason to believe it exists. Betting markets have suggested the world thinks it is more likely real than not. Andrew Griffin 8 hours ago comments the Tuesday session of the Demand Flexibility Service will come just 24 hours after the first live run took place between 5 p.m. and 6 p.m. on Monday. PA Archive. For free real-time breaking news alerts sent straight to your inbox, sign up to our breaking news emails. I would like to be emailed about offers, events, and updates from the Independent. Read our privacy notice. Excitement about a possibly revolutionary new material has continued to grow, even without any firm proof that it exists. Last week, 2 new papers published by researchers in South Korea claimed that they had been able to create a room temperature, ambient pressure superconductor. Until now, all superconductors have required cold temperatures and high pressure, and their practical use has been limited as a result. Such a breakthrough would achieve one of the holy grails of engineering and physics. It would allow for vastly more efficient energy transfer and the development of products such as powerful maglev trains. But almost as soon as the paper was released, experts urged caution about its findings. The claims in it could represent a significant breakthrough, but they were still far from confirmed, and similar reports have been released in the past that were later debunked. And there is still no clear indication that the breakthrough described in the original paper is definitely real. And despite numerous attempts to replicate the study, none have yet done so convincingly. Recommended. NASA just received a heartbeat from a missing spacecraft hundreds of years after it was discovered. One material could change the world. WorldCoin crypto launched by ChatGPT creator sees price surge. Some new work has suggested that the findings could at least be possible. In a new paper published on Monday, Sinead Griffin from Lawrence Berkeley National Laboratory simulated the material and suggested that it was at least theoretically possible. She shared the paper in a tweet accompanied by a mic drop gif. And it immediately had what was presumably the intended effect, leading to an increase in discussion of a topic that had already generated tremendous excitement. Around the same time, new videos appeared from China that claimed to show the work of a team who had successfully replicated the material. That showed the levitation effect that happens with superconductors, but not the low resistance that is required for the claims to be verified, and the material to be useful. Work to verify whether the original paper is correct and the material is actually as claimed is ongoing. But each of those videos only served to make the claims of a new breakthrough become louder, even as there was no firm proof that it had actually happened. For a period on Tuesday, the betting markets implied that the most likely result was that the papers would be replicated. Polymarket, a prediction market that lets people bet on a wide array of events, suggested that people tended to think there was a roughly 60% chance the result would be replicated, but a couple of hours later it slid back, and more bets had been placed on the outcome that the superconductor is not real.
Here is another article from Science Alert.
Radical superconductor claim sparks concern among scientists. Here's why. Physics, August 1, 2023 by Mahboobeh Shabazeh, The Conversation, Hyun Tak Kim. Last week, a group of South Korean physicists made a startling claim. In 2 papers uploaded to the AR-14 preprint server, they say they have created a material that opens a new era for humankind. LK99, a lead-based compound, is purportedly a room temperature, ambient pressure superconductor. Such a material, which conducts electricity without any resistance under normal conditions, could have huge implications for energy generation and transmission, transport, computing and other areas of technology. The papers have sparked wild enthusiasm online, and several efforts to replicate the work. At the same time, there are reports of disputes among the Korean researchers over whether the research should have been released at all. Why superconductors are so super? When an electric current flows through an ordinary conductor like a copper wire, the electrons bump into atoms as they jostle along. As a result, the electrons lose some energy and the wire heats up. In a superconductor, electrons move without any resistance. Superconducting wires can transmit electricity without losing energy, and superconducting magnets are powerful enough to levitate trains and contain the fierce plasmas in fusion reactors. However, all known superconductors require very low temperatures, typically lower than 100 degrees Celsius, for extremely high pressures, more than 100,000 times ordinary atmospheric pressure. These restrictions make superconductors expensive and impractical for many applications. Several teams of researchers have claimed to detect room temperature superconductivity in various substances in the past, but none of the claims have withstood scrutiny. As recently as last week, a superconductivity paper by American physicist Ranga Dias was retracted amid suspicions of data fabrication. So while a room temperature superconductor would be an amazing discovery, we should meet the new claims with some skepticism. Bold claims. The South Korean researchers say LK99 can be made in a baking process that combines the minerals lignarkite, Pb2SO5, and copper phosphide, Cu3P. They say the resulting material shows 2 key signs of superconductivity at normal air pressure and at temperatures up to 127 degrees Celsius, zero resistance and magnetic levitation. They propose a plausible theory of how LK99 might display room temperature superconductivity, but have not provided definite experimental evidence. The data presented in the papers appear inconclusive. One of the signatures of a superconductor is the Meissner effect, which causes it to levitate when placed above a magnet. In a video demonstration, the researchers position a piece of LK99 over a magnet. One edge of the flat disk of LK99 rises, but the other edge appears to maintain contact with the magnet. We would expect a superconductor to display full levitation and also quantum locking, which keeps it in a fixed position relative to the magnet. In a charitable interpretation, the behavior we see in the video may be due to imperfections in the sample, meaning only part of the sample becomes superconductive. So it is too early to say we have been presented with compelling evidence for room temperature superconductivity. What's next? At present, all we know about LK99 comes from the 2 AR-14 papers, which have not been peer-reviewed. Both papers present similar measurements, though the presentation is unconventional. However, there are some differences in the content, and also in authorship, which does not inspire confidence. So what happens now? The processes of science swing into action. Experts will closely review the papers. Researchers at other laboratories will attempt to reproduce the experiments described in the papers, and see whether they end up with a room temperature superconductor. These crucial steps are necessary to establish the validity and reliability of the LK99 claims. If the claims are validated and confirmed, it could mark one of the most groundbreaking advancements in physics and materials engineering in the past few decades. However, until the research undergoes rigorous review and testing, we should approach the claims with caution. We will all be awaiting the outcome of the verification process with great interest. Mahbub Shahbazi, Senior Research Fellow, Materials Science, Queensland University of Technology. This article is republished from The Conversation under a Creative Commons license. Read the original article. Trending news: scientists invented an entirely new process for refrigerating things. Tech 2 days ago, a giant planet seems to be lurking unseen in our solar system. Space 4 days ago, study finds that we can reduce our cancer risk thanks to vigorous everyday activities. Health 2 days ago. LK99 article. Talk, read, edit, view history tools from Wikipedia, the free encyclopedia. This article may be affected by a current scientific claim. Information in this article may change rapidly as the event progresses. Initial news reports may be unreliable. The last updates to this article may not reflect the most current information. Please feel free to improve this article, but note that updates without valid and reliable references will be removed, or discuss changes on the talk page. July 2023, learn how and when to remove this template message. LK99 3D structure identifiers 3D model, JSMOL, interactive image in CHI Smiles properties chemical formula CuO25P6PB9 molar mass 2514.2 g mol 1 appearance gray black solid density 6.699 g/cm31 structure crystal structure hexagonal space group P63/m number 176 lattice constant A equals 9.843 A, C equals 7.428 A lattice volume, V 623.283 formula units, Z 1 related compounds oxypyromorphite, lead apatite, except where otherwise noted. Data are given for materials in their standard state, at 25 degrees Celsius 77 degrees Fahrenheit, 100 kPa. Infobox references LK99 is a potential room temperature superconductor with a gray-black appearance 2.8. It has a hexagonal structure slightly modified from lead apatite, by introducing small amounts of copper. The material was first discovered and manufactured by a team of researchers including Suk-B Lee, and Ji-Hoon Kim, from Korea University 2.1. The team claims it functions as a superconductor at ambient pressure and below 400 K, 127 degrees Celsius, 260 degrees Fahrenheit. 321 As of August 2, 2023, the material has not been confirmed to be superconducting at any temperature. The synthesis of LK99 and observation of its superconductivity have not been peer-reviewed or independently replicated. The announcement was widely shared and the reaction by the scientific world was mainly skeptical due to the extraordinary nature of the claims and errors and inconsistencies in the pre-published papers. Independent teams are attempting to replicate the South Korean team's work, with results expected in August 2023 owing to the straightforward method of producing the material. The initial studies announcing the discovery were uploaded to the open access repository of electronic preprints AR14. Lee claimed that the uploaded preprint papers were incomplete. While co-author Hyun-Tak Kim stated that one of the papers contained defects. 7 Chemical properties. The chemical composition of LK99 is approximately Pb9Cu, Po4, 6O such that compared to pure lead apatite, Pb10, Po4, 6O, 8, 5 approximately 1/4 of Pb, 2, ions in position 2 of the apatite structure are replaced by Cu, 2, ions 2, 9 synthesis Li et al. Provide a method for chemical synthesis of Lk99 material 8, 2 by producing linarkite from a 1:1 molar mixing of lead, 2, oxide, PbO, and lead, 2, sulfate, Pb, so 4, powders, then heating at 725 degrees Celsius, 1000 K, 1340 degrees Fahrenheit, for 24 hours, PbO plus Pb, so 4, rightward arrow Pb2, so 4, O. Additionally, copper, I, phosphide, Cu3P, was produced by mixing copper, Cu, and phosphorus, P, powders in a 3:1 molar ratio in a sealed tube under a vacuum and heated to 550 degrees Celsius, 820 K, 1000 degrees Fahrenheit, for 48 hours 8, 3 Cu plus P rightward arrow Cu3P. Linarkite and copper phosphide crystals were ground into a powder, placed in a sealed tube under a vacuum, and heated to 925 degrees Celsius, 1200 K, 1700 degrees Fahrenheit, for between 520 hours 8, 3 Pb2, so 4, O plus Cu3P rightward arrow Pb10x cux, Po4, 6O plus S, G. Where, 0.9. 8. The internal stress is claimed to cause a heterojunction quantum well between the Pb1 and oxygen within the phosphate, Po43, generating a superconducting quantum well, SQW.2, 10 Li et al. Claim to show Lk99 exhibits a response to a magnetic field, potentially due to the Meissner effect, when chemical vapor deposition is used to apply Lk99 to a non-magnetic copper sample 2. 4. Pure lead apatite is an insulator, but Li et al. Claim copper-doped lead apatite forming Lk99 is a superconductor, or at higher temperatures, a metal. 8. 5. They do not claim to have observed any change in behavior across a transition temperature. Citation needed. The paper's mechanisms were based on a 2021 paper 9 by Hyun Tak Kim describing a novel BRBCS theory of superconductivity combining a classical theory of metal insulator transitions 10 with the standard Bardeen, Cooper, Schrieffer theory of superconductivity. The paper is far from mainstream physics, currently having fewer than 10 citations, and being published in Scientific Reports, a journal with a lax peer review and a history of controversial papers. They also use ideas from the theory of whole superconductivity 11 by J. E. Hirsch, another controversial work. On August 1, 2023, Sinead Griffin of Lawrence Berkeley National Laboratory published a preprint analyzing the reported structure of Lk99 with density functional theory and the Vienna ab initio simulation package. This analysis suggested a potential mechanism for copper-substituted lead apatite to develop correlated isolated flat bands, a common signature of high transition temperature superconductors. 12. Compound name. The name Lk99 is from the initials of discoverers Suk-bae Lee and Ji-hoon Kim, and the year of discovery, 1999. 13. The pair had originally been working with Professor Tong-Shik Choi, at Korea University in the 1990s. 14. In 2008, researchers from Korea University founded the Quantum Energy Research Center, also known as Q Center. 6. Lee would later become CEO of Q Center, and Kim would become Director of Research and Development, R&D, at Q Center. When Tong-Shik Choi died in 2017, he requested in his will that Lk99 research be continued. Q Center got new funding in the same year and interest in Lk99 research was renewed in 2018. Citation needed. Publication history. In 2020, an initial paper was submitted to Nature, but it was rejected. 14. Similarly presented research on room temperature superconductors by Ranga P. Dias had been published in Nature earlier that year, and received with skepticism. Dias's paper would subsequently be retracted in 2022 after its data was found to have been falsified. 15. In 2020, Lee and Ji-hoon Kim filed a patent application. 16. A second patent application, Additionally, listing Kwon was filed in 2021, which was published on 3 March 2023, 17 on April 4, 2023. A Korean trademark application for LK99 was filed by the Q Center 18 in February 2023. The Q Center published a video on YouTube claiming to show the magnetic properties of a thin layer of LK99 thermally deposited on a copper plate. 19 scholarly articles and preprints. A series of academic publications summarizing initial findings came out in 2023, with a total of 7 authors across 4 publications. On March 31, 2023, a Korean language paper, Consideration for the Development of Room Temperature Ambient Pressure Superconductor, LK99, was submitted to the Korean Journal of Crystal Growth and Crystal Technology 3. It was accepted on April 18, but was not widely read until 3 months later. On July 22, 2023, 2 preprints appeared on AR14. One listed Youngwon Kwon, former Q Center CTO, as third author. A second preprint listed as third author Hyun-Tak Kim, former principal researcher at the Electronics and Telecommunications Research Institute and professor at the College of William and Mary. On July 23, the findings were also submitted to APL Materials for peer review. 14.6 On July 28, 2023, Kwon presented the findings at a symposium held at Korea University 2021-22. That same day, Yonhap News Agency published an article quoting an official from Korea University as saying that Kwon was no longer in contact with the university. 6 The article also quoted Lee saying that Kwon had left the Q Center Research Institute 4 months previously. 6 That the academic papers on LK99 were not finished, and that the papers had been uploaded to AR14 without the other author's permission. 6 On July 31, a group led by Kapil Kumar published a preprint on AR14 documenting their replication attempts, which confirmed the structure using X-ray crystallography, XRD, but failed to find diamagnetism or levitation. 23 On August 1, 2023, a Q Center representative told SBS News that the original samples referenced in the paper would be released to the world for verification soon. 24 Authors. Author credit and affiliation matrix. Author affiliation: Lee, Suk-bi, Kim, Ji-hoon, Kim, Hyun-Tak, Im, Sung-yeon, and Soo-min, Kwon, Youngwon, Ah, Hyun-ho, Choi. Tong-shik, HYU Professor Emeritus. Kukist, former research professor. 6 WNM Professor. Q Center, CEO R&D Director. Yes former CTO. 6 CTO Patent, 2020, 1612 Patent, 2021, 17123 Lee and Kim Plus, April 18, 2023, 3123456 Acknowledged Lee and Kim Plus, 22 July 2023. A 212 Acknowledged 3 Acknowledged Lee and Kim Plus, 22 July 2023. B 812345 Acknowledged 6 Acknowledged 1 equals first author, 2 equals second author, etc. Response materials. Scientists and superconductor researchers responded with skepticism. 7 The highest temperature superconductors known at the time of publication had a critical temperature of 250 K, 23 degrees C, 10 degree F, at pressures of over 170 gigapascals, 1,680,000 atm, 24,700,000 psi. The highest temperature superconductors at atmospheric pressure, 1 atm, had a critical temperature of at most 150 K, minus 123 degrees Celsius, minus 189 degrees Fahrenheit. One of the strongest criticisms comes from the quantum aspect of the electrons running through the superconductor. 25 Both electrons having the same spin is necessary for the electrons to function as pure energy with quantum mechanics, and the internal space proposed in LK99 may not be able to produce the quantum wells that the SK team think it does. 26. As of August 1, 2023, the measured properties do not prove that LK99 is a superconductor, as the published material does not fully explain how the LK99's magnetization can change, demonstrate its specific heat capacity, or demonstrate it crossing its transition temperature. 7. An alternative explanation for LK99 stated partial magnetic levitation could be solely from non-superconductive diamagnetism. 27. Replication attempts. This article relies excessively on references to primary sources. Please improve this article by adding secondary or tertiary sources. Find sources: LK99, News Newspapers Book Scholar Jaster, August 2023, learn how and when to remove this template message. As of August 1, 2023, the experiment had not been successfully replicated, despite the initial experiments being completed in 2020. After the July 2023 publication's release, independent groups reported that they had begun attempting to reproduce the synthesis, with initial results expected within weeks. 5. However, while positive results can come quickly, negative results are slow, as falsification needs to verify all possibilities, and it will take a lot of time. 28. The first attempts that published results did not observe levitation or diamagnetism, and their samples had high resistivity. A Chinese team at Huazhong University of Science and Technology reported producing tiny flakes that showed diamagnetic levitation. On their second attempt, 29 none produced enough to test resistivity, flux pinning, or specific heat. This list is incomplete. You can help by adding missing items. August 2023, Group Country Status Result References Notes. Huazhong University of Science and Technology China results unavailable. 8/1, video claiming to show diamagnetism of small. Beihang University China preliminary results available, no levitation or diamagnetism observed. High resistivity measurements taken not consistent with superconductivity. 32 Li Lu, ETALAR 14. Council of Scientific and Industrial Research, National Physical Laboratory of India, CSIRNPLI, India preliminary results available, no levitation or diamagnetism observed, plausibly due to challenging Cu doping. Structure confirmed by XRD23 Kapil Kumar, ETAL verified authors 3334 AR14. Southeast University China preliminary results available, no diamagnetism or levitation observed. 3528 Professor Sun Yu, et al. Argonne National Laboratory United States unknown. 36 Nanjing University China unknown. 37 College de France, Solid State Chemistry and Energy Lab France partial failure, Meissner effect not observed in quenched sample. 38 Second sample and X-ray analysis in progress. 39 40 41 42 Original research PhD student on Twitter, in the lab of Jean-Marie Tarascon. Varda Space Industries and University of Southern California United States unknown. 43 Original research engineer and entrepreneur on Twitter. Theoretical studies in the initial papers. The theoretical explanations for potential mechanisms of superconductivity in LK99 were incomplete. Later analyses by other labs have added further simulations and theoretical evaluations of the material's electronic properties from first principles. This list is incomplete. You can help by adding missing items. August 2023, Group Country Status Result References Notes. Chinese Academy of Sciences Shenyang National Laboratory for Materials Science, SYNL, China Theoretical Study available, First Principles Study of the electronic structure of LK99 and other variants. Expresses no opinion on room temp superconductivity, but suggests gold-doped apatite may have stronger effects. 44 Junwen Lai, ETAL, AR14. Lawrence Berkeley National Laboratory United States Theoretical Study available, density functional theory calculations on a simplified 3D structure explores possible electronic structure that could be favorable for superconductivity, and slightly decrease the lattice constant. 1245-46 Sinead Griffin, AR14. Tübingen Austria Theoretical Study available, density functional theory calculations of electronic structure shows possible support of superconductivity when doped. Theory does not support diamagnet without superconductivity. 47 Liang S.I. and Karsten Held, AR14. University of Colorado Boulder, National Renewable Energy Laboratory and King's College London, United States and United Kingdom. Theoretical study available density functional theory calculations of electronic structure shows potential for superconductivity or other novel electronic physics. Suggests weak interaction of copper-oxygen while minimizing hybridization, shows promise for high-temperature superconductivity, regardless of realization of LK99. 48 Revolker-Leto, ETAL, AR14. References 2514.2 AMU/Sin, 60 degrees, 9.843 9.843 *7.428 A*3. Wolfram Alpha, calculation. Archived from the original on July 29, 2023. Retrieved July 29, 2023. Lee, Suk-B, Kim, Ji-hoon, Kwon, Youngwon, July 22, 2023. The first room temperature ambient pressure superconductor. AR14 2307.12008. Lee, Suk-B, Kim, Ji-hoon, Im, Sung-yeon, and Sumin, Kwon, Youngwon, Kyun-ho, March 31, 2023. Consideration for the development of room temperature ambient pressure superconductor, LK99. Korean Crystal Growth and Crystal Technology. Korea Association of Crystal Growth. 33, 26170 doi 10.6111/JKCGCT.2023.33.2.061. Archived from the original on July 25, 2023. Retrieved July 25, 2023. Flaherty, Nick, July 26, 2023. Race is on for room temperature superconductor. Technology News. EE News Europe. European Business. Archived from the original on July 26, 2023. Retrieved July 26, 2023. Published on the preprint server ar14.org and still has to go through peer review. Garisto, Dan, July 27, 2023. Viral new superconductivity claims leave many scientists skeptical. Materials Science. Scientific American. Archived from the original on July 27, 2023. Retrieved July 28, 2023. July 28, 2023. Ed. Controversy both domestic and abroad regarding Korean development of room temperature superconductor. It has to be verified, in Korean. Yonhap News Agency. Archived from the original on July 28, 2023. Retrieved July 28, 2023. CTO, 4. Budovic Callahan, Carmela, July 26, 2023. Room temperature superconductor breakthrough met with skepticism. New Scientist. Archived from the original on July 26, 2023. Retrieved July 26, 2023. Speaking to New Scientist, Hyun-Tak Kim at the College of William and Mary in Virginia says he will support anyone trying to replicate his team's work. H.T. Kim has only co-authored one of the AR14 papers, while the other is authored by his colleagues at the Quantum Energy Research Center in South Korea. Both papers present similar measurements, however H.T. Kim says that the second three-author paper contains many defects and was uploaded to AR14 without his permission. Once the findings are published in a peer-reviewed journal, H.T. Kim says, he will support anyone who wants to create and test LK99. Lee, Suk-B, Kim, Ji-hoon, Kim, Hyun-Tak, Im, Sung-yeon, and Sumin, Kyun-ho, July 22, 2023. Superconductor PB10X Cox, Po460 showing levitation at room temperature and atmospheric pressure and mechanism. AR14 2307.12037. Kim, Hyun-Tak, May 14, 2021. Room temperature superconducting DC driven by electron correlation. Scientific reports. 11, 110329 doi 10.1038/S41598-021-88937-7. ISSN 2045-2322. Brinkman, W.F., Rice, T.M., November 15, 1970. Application of Gutzwiller's variational method to the metal insulator transition. Physical Review B2, 104302-4304 doi 10.1103/Physical Rev B.2.4302. ISSN 0556-2805. Hirsch, J.E., January 23, 1989. Hole superconductivity. Physics Letters A134, 7451-455 doi 10.1016/0375-9601, 89, 90370-8. ISSN 0375-9601. Griffin, Sinead M., July 31, 2023. Origin of correlated isolated flat bands in copper substituted lead phosphate apatite. AR 142307.16892 Con Mat. Sapir Khan. Kim, Ji Hoon. About. Retrieved July 26, 2023. Working on superconducting materials again, and finally, succeeded in synthesizing a room temperature and atmospheric pressure superconductor, RTAPSC, named LK99, first discovered as a trace by Dr. Lee and Dr. Kim in 1999. July 27, 2023. Korean study into world's first room temperature superconductor, can it overcome scientific skepticism, to win Nobel Prize? Chosen Biz, in Korean. Archived from the original on July 27, 2023. Retrieved July 27, 2023. 272020. 23 Alp. 199020. Garisto, Dan, July 25, 2023. A very disturbing picture, another retraction imminent for controversial physicist. Nature. doi 10.1038/D41586-023-02401-2. Archived from the original on July 27, 2023. Retrieved July 28, 2023. KR Application 20210062550A, and Method of manufacturing ceramic composite with low resistance including superconductors and the composite thereof, published June 2, 2022. KR published 20230275536A1, and Ceramic composite with superconductivities over room temperature at atmospheric condition and method of manufacturing the ceramic composite, published March 2, 2023. Archived July 26, 2023 at the Wayback Machine LK99. Korea Intellectual Property Rights Information Service, Report. Korean Intellectual Property Office. April 4, 2023. Archived from the original on July 26, 2023. Retrieved July 25, 2023. LK99. Applicant, Quantum Energy Research Center, Q Center. Status, awaiting examination magnetic property test of LK99 film. Q Center retrieved August 2, 2023, via YouTube. Recorded on January 26, 2023. The sample was thermally deposited on a copper plate. Kwon, Youngwon, July 28, 2023. The world first, room temperature ambient pressure superconductor. MML 2023, 11th International Symposium on Metallic Multilayers, Conference Presentation. Korea University, Seoul, Korea, the Korean Magnetics Society. Seifert, Tom S. at Teratom_S, July 28, 2023. Just listening to an impressive talk of one of the co-authors of the room temperature superconductor #LK99 at Korea University, Youngwon Kwon, tweet. Retrieved July 28, 2023, via Twitter. Bowden, Kenneth at Kenneth Bowden, July 28, 2023. They have now also presented at MML 2023. They took questions. Answers not entirely satisfying. Rumor is that MIT SC specialists are flying over to scrutinize experiments. Photo at Johanna Ackerman. Yoa Ackerman, tweet. Retrieved July 28, 2023, via Twitter. Kumar, Kapil, July 31, 2023. Synthesis of possible room temperature superconductor LK99PB9Cu, PO4, 60. AR14 2307.16402. Zhang, Guhe, August 1, 2023. Development of dream material. Superconductor hot interest. Sample to be released soon. SBS 8 News, video, offset 220, in Korean. Seoul Broadcasting System, SBS. Retrieved August 1, 2023, via YouTube. Reported failure to reproduce superconductivity at room temperature in LK99 Science 2.0. www.science20.com August 27, 2014. Retrieved August 1, 2023. Possibly the beginning of quantum well superconductors nextbigfuture.com. July 27, 2023. Retrieved August 1, 2023. Ritchie, Stuart, July 26, 2023. The latest mega breakthrough on room temperature superconductors is probably nonsense. I archived from the original on July 26, 2023. Retrieved July 27, 2023. What about that levitation video? Dr. Sven Friedemann, Associate Professor at the University of Bristol School of Physics, told I that it, and other data in the paper, could stem from other phenomena. Graphene is also diamagnetic, displaying repulsion like a superconductor and can produce weak levitation. The video, in other words, could have a non-superconductor explanation. __Bilibili. www.bilibili.com, in simplified Chinese. Retrieved July 31, 2023. Low, Derek, August 1, 2023. Chemical News, a room temperature superconductor? New developments. Science.org in the pipeline, blog. Science, Journal. Retrieved August 1, 2023. LK99 __Bilibili. www.bilibili.com, in simplified Chinese. Retrieved August 1, 2023. __Bilibili. www.bilibili.com, in simplified Chinese. Retrieved August 1, 2023. Li Lu, Xiang Men, Xiaoning Wang, Hongyu Chen, Zaiwen Duan, Xiaorongzhou, Han Yan, Paizhen Qin, Zhaiki Lu, July 31, 2023. Semiconducting transport in PB10X CUX, PO4, 60 sintered from PB2SO5 and Cu3P. AR14 2307.16802 Condmat.Sapir People at CSIR NPL. Retrieved July 31, 2023. Dr. VPS Awana, PhD, Editorial Board, Superconductivity, Journal, Elsevier. www.journals.elsevier.com. Retrieved July 31, 2023. www.scscu.cn. Retrieved July 31, 2023. Cho, Adrian, July 27, 2023. A spectacular superconductor claim is making news. Here's why experts are doubtful. Physics News. Science.org, American Association for the Advancement of Science. DOI 10.1126/science.adk0021. Archived from the original on July 29, 2023. Retrieved July 29, 2023. Michael Norman, a theorist at Argonne National Laboratory, says, researchers at Argonne and elsewhere are already trying to replicate the experiment. News.sciencenet.cn. Archived from the original on July 31, 2023. Retrieved July 31, 2023. At Zuberas0595, August 1, 2023. Reddish pellet came out of the quartz tube after quenching. Probably not the best strategy since the sulfur would just react back with the copper and form more impurities. Meissner effect not observed in both bulk and small bits of the sample, tweet. Retrieved August 1, 2023, via Twitter. At Zuberas0595, August 1, 2023. We still have another sample that we will cool at 5 degrees C/min, completely random rate since they don't specify in the paper, which can be crucial to the phase formation, tweet. Retrieved August 1, 2023, via Twitter. At Zuberas0595, July 31, 2023. We're trying to replicate it in my lab over here in Paris. We are making our own precursors to ensure purity, tweet. Retrieved July 31, 2023, via Twitter. At Zuberas0595, July 31, 2023. Collège de France. Jean-Marie Tarascon's lab. Tweet. Retrieved July 31, 2023, via Twitter. PhD students. Solid State Chemistry and Energy Lab, September 12, 2019. Retrieved July 31, 2023. At Andromacolib, July 31, 2023. Meissner effect or bust, day 4, tweet. Retrieved August 1, 2023, via Twitter. Lai, Junwen, Jiangxiu, Li, Haitao, Lu, Yan, Sun, Xin Qiu, Chen, July 29, 2023. First principle study on the electronic structure of PB10X CUX, Po4, 60, X equals 0, 1. AR14 2307.16040 Condmat.mtrl Sci. At Michaels Führer, August 1, 2023. This isn't the kind of paper that will get the physicists any more excited about the prospect of the result, room T superconductivity, being correct, tweet. Retrieved August 1, 2023, via Twitter. Condensed Matter Theory Center, UMD at condensed_the, August 1, 2023. For such flat band systems, packaged LDA type calculations are of limited utility, but knowing the LDA band structure is again a small, but necessary, step in understanding the physics. Flat bands do not imply SC, flat bands often lead to magnetic instabilities, tweet. Retrieved August 2, 2023, via Twitter. SI, Liang, Held, Karsten, August 1, 2023. Electronic structure of the putative room temperature superconductor PB9Cu, Po4, 60. AR14 2308.006766 Condmat.Sapir Con. Carlito, Rafal, Laney, Stefan, Pashev, Dimitar, Acharya, Svogta, Vanskilf Giard, Mark, Dessau, Daniel S., August 1, 2023. PB Appetite Framework as a generator of novel flat-band CuO-based physics, including possible room temperature superconductivity. AR14 2308.00698 Condmat.Sapir Con. Further reading, May 17, 1994. Theoretical Framework of the Superconducting Revolution, in Korean. ISBN 89-7641-276-1. Archived from the original on July 27, 2023. Retrieved July 27, 2023. Krivovyshev, Sergey V., Burns, Peter C., October 17, 2002. Crystal chemistry of lead oxide phosphates, crystal structures of Pb40, Po4, 2, Pb805, Po4, 2 and Pb10, Po4, 60. Zeitschrift für Kristallography, Crystalline Materials. Munich, Oldenburg Wissenschaftsverlag, published May 1, 2003. DOI 10.15.4/3.218.5.357.20732. The compound Pb10, Po4, 60 has been designated oxypyromorphite. Pb10, Po4, 60 crystallizes with an apatite-type structure. The structure contains a single O atom that is not part of a Po4 tetrahedron. It has a site occupancy factor of 0.25 and is located on the 63 axis. Lowe, Derek, July 26, 2023. Breaking superconductor news. Chemical news. In the Pipeline, blog. American Association for the Advancement of Science. Archived from the original on July 26, 2023. Retrieved July 26, 2023, via science.org. Orff, Darren, July 27, 2023. Scientists claim they found the holy grail of superconductors. Energy. Popular Mechanics. Retrieved July 28, 2023. Harris, Margaret, July 27, 2023. Have scientists in Korea discovered the first room temperature, ambient pressure superconductor? Superconductivity blog. Physics World. Institute of Physics. Archived from the original on July 28, 2023. Retrieved July 29, 2023. External links. Official website archived August 1, 2023 at the Wayback Machine magnetic property test of LK99 film, video. Quantum Energy Research Center. January 26, 2023. Retrieved July 25, 2023, via YouTube. This effect is a conductive copper plate induced by a magnetic. Kim, Hyun Tak, July 25, 2023. Superconductor Pb10X CUX, Po4, 60 showing levitation at room temperature and atmospheric pressure and mechanism, video. Retrieved July 25, 2023, via sciencecast.archive July 31, 2023 at the Wayback Machine.
Well, that was interesting.
Contents hide, top, classification toggle classification subsection response to a magnetic field by theory of operation
another
by
article.
critical temperature by material elementary properties of superconductors toggle elementary properties of superconductors subsection 0 electrical DC resistance phase transition Meissner effect London moment history toggle history subsection London constitutive equations conventional theories, 1950s. Further history high temperature superconductivity applications Nobel Prizes for superconductivity. See also references. Further reading. External link. Superconductivity article. Talk, read, edit, view history tools from Wikipedia. The free encyclopedia. Articles about electromagnetism, electricity, magnetism, optics, history, textbooks, electrostatics, magnetostatics, electrodynamics, electrical network, magnetic circuit, covariant formulation. Scientists beat a magnet levitating above a high-temperature superconductor, cooled with liquid nitrogen. Persistent electric current flows on the surface of the superconductor, acting to exclude the magnetic field of the magnet, Faraday's law of induction. This current effectively forms an electromagnet that repels the magnet. Video of the Meissner effect in a high-temperature superconductor, black pellet, with the NdFeB magnet, metallic, a high-temperature superconductor levitating above a magnet. Superconductivity is a set of physical properties observed in certain materials where electrical resistance vanishes and magnetic flux fields are expelled from the material. Any material exhibiting these properties is a superconductor. Unlike an ordinary metallic conductor, whose resistance decreases gradually as its temperature is lowered, even down to near absolute zero, a superconductor has a characteristic critical temperature below which the resistance drops abruptly to 0.12. An electric current through a loop of superconducting wire can persist indefinitely with no power source. 3456. The superconductivity phenomenon was discovered in 1911 by Dutch physicist Heike Kamerlingh-Onnes. Like ferromagnetism and atomic spectral lines, superconductivity is a phenomenon which can only be explained by quantum mechanics. It is characterized by the Meissner effect, the complete ejection of magnetic field lines from the interior of the superconductor during its transitions into the superconducting state. The occurrence of the Meissner effect indicates that superconductivity cannot be understood simply as the idealization of perfect conductivity in classical physics. In 1986, it was discovered that some cuprate perovskite ceramic materials have a critical temperature above 90 K, 183 degrees C. 7 Such a high transition temperature is theoretically impossible for a conventional superconductor, leading the materials to be termed high-temperature superconductors. The cheaply available coolant liquid nitrogen boils at 77 K, 196 degrees C, and thus the existence of superconductivity at higher temperatures than this facilitates many experiments and applications that are less practical at lower temperatures. Classification. Main article, Superconductor classification. There are many criteria by which superconductors are classified. The most common are: response to a magnetic field. A superconductor can be type I, meaning it has a single critical field, above which all superconductivity is lost and below which the magnetic field is completely expelled from the superconductor, or type II, meaning it has two critical fields, between which it allows partial penetration of the magnetic field through isolated points. 8 These points are called vortices. 9 Furthermore, in multi-component superconductors it is possible to have a combination of the two behaviors. In that case the superconductor is of type 1.510. By theory of operation it is conventional if it can be explained by the BCS theory or its derivatives, or unconventional, otherwise. 11 Alternatively, a superconductor is called unconventional if the superconducting order parameter transforms according to a non-trivial irreducible representation of the point group or space group of the system. By critical temperature, a superconductor is generally considered high temperature if it reaches a superconducting state above a temperature of 30 K, 243.15 degrees C, 12 as in the initial discovery by George Bednorz and K. Alex Muller. 7 It may also reference materials that transition to superconductivity when cooled using liquid nitrogen, that is, at only Tc 77 K, although this is generally used only to emphasize that liquid nitrogen coolant is sufficient. Low-temperature superconductors refer to materials with a critical temperature below 30 K, and are cooled mainly by liquid helium, Tc 4.2 K. One exception to this rule is the iron-nictide group of superconductors, which display behavior and properties typical of high-temperature superconductors, yet some of the group have critical temperatures below 30 K. By material top, periodic table of superconducting elemental solids and their experimental critical temperature, T. Bottom, periodic table of superconducting binary hydrides, 0 to 300 GPa. Theoretical predictions indicated in blue and experimental results in red. 13 superconductor material classes include chemical elements, e.g. mercury or lead, alloys, such as niobium, titanium, germanium, niobium, and niobium nitride, ceramics, YbCO and magnesium diboride, superconducting pnictides, like fluorine-doped LaOFAs, or organic superconductors, fullerenes and carbon nanotubes, though perhaps these examples should be included among the chemical elements, as they are composed entirely of carbon. 1415 Elementary properties of superconductors. This section needs additional citations for verification. Please help improve this article by adding citations to reliable sources in this section. Unsourced material may be challenged and removed. Find sources: Superconductivity, News Newspapers Books Scholar Jaster, April 2018, Learn how and when to remove this template message. Several physical properties of superconductors vary from material to material, such as the critical temperature, the value of the superconducting gap, the critical magnetic field, and the critical current density at which superconductivity is destroyed. On the other hand, there is a class of properties that are independent of the underlying material. The Meissner effect, the quantization of the magnetic flux or permanent currents, i.e. the state of zero resistance, are the most important examples. The existence of these universal properties is rooted in the nature of the broken symmetry of the superconductor and the emergence of off-diagonal long-range order. Superconductivity is a thermodynamic phase, and thus possesses certain distinguishing properties which are largely independent of microscopic details. Off-diagonal long-range order is closely connected to the formation of Cooper pairs. An article by B.F. Weisskopf presents simple physical explanations for the formation of Cooper pairs, for the origin of the attractive force causing the binding of the pairs, for the finite energy gap, and for the existence of permanent currents. 16.0 Electrical DC resistance electric cables for accelerators at SERB. Both the massive and slim cables are rated for 12,500 A top, regular cables for left, bottom, superconductor-based cables for the LHC cross-section of a preformed superconductor rod from the abandoned Texas Superconducting Super Collider, SSC. The simplest method to measure the electrical resistance of a sample of some material is to place it in an electrical circuit in series with the current source I and measure the resulting voltage V across the sample. The resistance of the sample is given by Ohm's law as R equals V/I. If the voltage is zero, this means that the resistance is zero. Superconductors are also able to maintain a current with no applied voltage whatsoever, a property exploited in superconducting electromagnets such as those found in MRI machines. Experiments have demonstrated that currents in superconducting coils can persist for years without any measurable degradation. Experimental evidence points to a lifetime of at least 100,000 years. Theoretical estimates for the lifetime of a persistent current can exceed the estimated lifetime of the universe, depending on the wire geometry and the temperature. 5 In practice, currents injected in superconducting coils have persisted for more than 27 years, as of August 2022, in superconducting gravimeters 1718. In such instruments, the measurement is based on the monitoring of the levitation of a superconducting niobium sphere with a mass of 4 grams. In a normal conductor, an electric current may be visualized as a fluid of electrons moving across a heavy ionic lattice. The electrons are constantly colliding with the ions in the lattice, and during each collision some of the energy carried by the current is absorbed by the lattice and converted into heat, which is essentially the vibrational kinetic energy of the lattice ions. As a result, the energy carried by the current is constantly being dissipated. This is the phenomenon of electrical resistance and Joule heating. The situation is different in a superconductor. In a conventional superconductor, the electronic fluid cannot be resolved into individual electrons. Instead, it consists of bound pairs of electrons known as Cooper pairs. This pairing is caused by an attractive force between electrons from the exchange of phonons. This pairing is very weak, and small thermal vibrations can fracture the bond. Due to quantum mechanics, the energy spectrum of this Cooper pair fluid possesses an energy gap, meaning there is a minimum amount of energy delta E that must be supplied in order to excite the fluid. Therefore, if delta E is larger than the thermal energy of the lattice, given by kT, where K is the Boltzmann constant and T is the temperature, the fluid will not be scattered by the lattice. 19 The Cooper pair fluid is thus a superfluid, meaning it can flow without energy dissipation. In the class of superconductors known as type II superconductors, including all known high-temperature superconductors, an extremely low but non-zero resistivity appears at temperatures not too far below the nominal superconducting transition when an electric current is applied in conjunction with a strong magnetic field, which may be caused by the electric current. This is due to the motion of magnetic vortices in the electronic superfluid, which dissipates some of the energy carried by the current. If the current is sufficiently small, the vortices are stationary, and the resistivity vanishes. The resistance due to this effect is minuscule compared with that of non-superconducting materials, but must be taken into account in sensitive experiments. However, as the temperature decreases far enough below the nominal superconducting transition, these vortices can become frozen into a disordered but stationary phase known as a vortex glass. Below this vortex glass transition temperature, the resistance of the material becomes truly zero. Phase transition behavior of heat capacity, CV, blue, and resistivity, ρ, green, at the superconducting phase transition in superconducting materials. The characteristics of superconductivity appear when the temperature T is lowered below a critical temperature Tc. The value of this critical temperature varies from material to material. Conventional superconductors usually have critical temperatures ranging from around 20 K to less than 1 K. Solid mercury, for example, has a critical temperature of 4.2 K. As of 2015, the highest critical temperature found for a conventional superconductor is 203 K for H2S, although high pressures of approximately 90 gigapascals were required. 20 cuprate superconductors can have much higher critical temperatures. YBA2Cu307, one of the first cuprate superconductors to be discovered, has a critical temperature above 90 K, and mercury-based cuprates have been found with critical temperatures in excess of 130 K. The basic physical mechanism responsible for the high critical temperature is not yet clear. However, it is clear that a two-electron pairing is involved, although the nature of the pairing, wave Bs wave, remains controversial. 21 Similarly, at a fixed temperature below the critical temperature, superconducting materials cease to superconduct when an external magnetic field is applied which is greater than the critical magnetic field. This is because the Gibbs free energy of the superconducting phase increases quadratically with the magnetic field while the free energy of the normal phase is roughly independent of the magnetic field. If the material superconducts in the absence of a field, then the superconducting phase free energy is lower than that of the normal phase, and so for some finite value of the magnetic field, proportional to the square root of the difference of the free energies at zero magnetic field, the two free energies will be equal and a phase transition to the normal phase will occur. More generally, a higher temperature and a stronger magnetic field lead to a smaller fraction of electrons that are superconducting and consequently to a longer London penetration depth of external magnetic fields and currents. The penetration depth becomes infinite at the phase transition. The onset of superconductivity is accompanied by abrupt changes in various physical properties, which is the hallmark of a phase transition. For example, the electronic heat capacity is proportional to the temperature in the normal, non-superconducting, regime. At the superconducting transition, it suffers a discontinuous jump and thereafter ceases to be linear. At low temperatures, it varies instead as E alpha/T for some constant, alpha. This exponential behavior is one of the pieces of evidence for the existence of the energy gap. The order of the superconducting phase transition was long a matter of debate. Experiments indicate that the transition is second order, meaning there is no latent heat. However, in the presence of an external magnetic field there is latent heat, because the superconducting phase has a lower entropy below the critical temperature than the normal phase. It has been experimentally demonstrated 22 that, as a consequence, when the magnetic field is increased beyond the critical field, the resulting phase transition leads to a decrease in the temperature of the superconducting material. Calculations in the 1970s suggested that it may actually be weakly first order due to the effect of long-range fluctuations in the electromagnetic field. In the 1980s it was shown theoretically with the help of a disorder field theory, in which the vortex lines of the superconductor play a major role, that the transition is of second order within the type II regime and of first order, i.e., latent heat, within the type I regime, and that the two regions are separated by a tricritical point 23. The results were strongly supported by Monte Carlo computer simulations. 24 Meissner effect. Main article, Meissner effect. When a superconductor is placed in a weak external magnetic field H, and cooled below its transition temperature, the magnetic field is ejected. The Meissner effect does not cause the field to be completely ejected, but instead, the field penetrates the superconductor but only to a very small distance, characterized by a parameter lambda, called the London penetration depth, decaying exponentially to zero within the bulk of the material. The Meissner effect is a defining characteristic of superconductivity. For most superconductors, the London penetration depth is on the order of 100 nanometers. The Meissner effect is sometimes confused with the kind of diamagnetism one would expect in a perfect electrical conductor. According to Lenz's law, when a changing magnetic field is applied to a conductor, it will induce an electric current in the conductor that creates an opposing magnetic field. In a perfect conductor, an arbitrarily large current can be induced, and the resulting magnetic field exactly cancels the applied field. The Meissner effect is distinct from this. It is the spontaneous expulsion that occurs during transition to superconductivity. Suppose we have a material in its normal state, containing a constant internal magnetic field. When the material is cooled below the critical temperature, we would observe the abrupt expulsion of the internal magnetic field, which we would not expect based on Lenz's law. The Meissner effect was given a phenomenological explanation by the brothers Fritz and Heinz London, who showed that the electromagnetic free energy in a superconductor is minimized provided 2 equals 2, where H is the magnetic field and lambda is the London penetration depth. This equation, which is known as the London equation, predicts that the magnetic field in a superconductor decays exponentially from whatever value it possesses at the surface. A superconductor with little or no magnetic field within it is said to be in the Meissner state. The Meissner state breaks down when the applied magnetic field is too large. Superconductors can be divided into 2 classes according to how this breakdown occurs. In type I superconductors, superconductivity is abruptly destroyed when the strength of the applied field rises above a critical value Hc. Depending on the geometry of the sample, one may obtain an intermediate state 25 consisting of a Baroque pattern 26 of regions of normal material carrying a magnetic field mixed with regions of superconducting material containing no field. In type II superconductors, raising the applied field past a critical value Hc1 leads to a mixed state, also known as the vortex state, in which an increasing amount of magnetic flux penetrates the material, but there remains no resistance to the flow of electric current as long as the current is not too large. At a second critical field strength Hc2, superconductivity is destroyed. The mixed state is actually caused by vortices in the electronic superfluid, sometimes called fluxons because the flux carried by these vortices is quantized. Most pure elemental superconductors, except niobium and carbon nanotubes, are type I, while almost all impure and compound superconductors are type II. London moment. Conversely, a spinning superconductor generates a magnetic field, precisely aligned with the spin axis. The effect, the London moment, was put to good use in Gravity Probe B. This experiment measured the magnetic fields of 4 superconducting gyroscopes to determine their spin axes. This was critical to the experiment since it is one of the few ways to accurately determine the spin axis of an otherwise featureless sphere. History. Main article, History of Superconductivity. Heike Kamerling Onus, Wright, the discoverer of superconductivity. Paul Ehrenfest, Hendrik Lorentz, Niels Bohr stand to his left. Superconductivity was discovered on April 8, 1911 by Heike Kamerlingh Onnes, who was studying the resistance of solid mercury at cryogenic temperatures using the recently produced liquid helium as a refrigerant 27 at the temperature of 4.2 K. He observed that the resistance abruptly disappeared 28 in the same experiment. He also observed the superfluid transition of helium at 2.2 K, without recognizing its significance. The precise date and circumstances of the discovery were only reconstructed a century later, when Onnes's notebook was found. 29 in subsequent decades, superconductivity was observed in several other materials. In 1913, lead was found to superconduct at 7 K, and in 1941 niobium nitride was found to superconduct at 16 K. Great efforts have been devoted to finding out how and why superconductivity works. The important step occurred in 1933, when Meissner and Oxenfeld discovered that superconductors expelled applied magnetic fields, a phenomenon which has come to be known as the Meissner effect. 30 in 1935, Fritz and Heinz London showed that the Meissner effect was a consequence of the minimization of the electromagnetic free energy carried by superconducting current. 31 London constitutive equations. The theoretical model that was first conceived for superconductivity was completely classical. It is summarized by London constitutive equations. It was put forward by the brothers Fritz and Heinz London in 1935, shortly after the discovery that magnetic fields are expelled from superconductors. A major triumph of the equations of this theory is their ability to explain the Meissner effect. 30 wherein a material exponentially expels all internal magnetic fields as it crosses the superconducting threshold. By using the London equation, one can obtain the dependence of the magnetic field inside the superconductor on the distance to the surface. 32 The two constitutive equations for a superconductor by London are equals 2 times equals 2. The first equation follows from Newton's second law for superconducting electrons. Conventional theories, 1950s. During the 1950s, theoretical condensed matter physicists arrived at an understanding of conventional superconductivity, through a pair of remarkable and important theories, the phenomenological Ginzburg-Landau theory, 1950, and the microscopic BCS theory, 1957. 33-34 In 1950, the phenomenological Ginzburg-Landau theory of superconductivity was devised by Landau and Ginzburg. 35 This theory, which combined Landau's theory of second-order phase transitions with a Schrödinger-like wave equation, had great success in explaining the macroscopic properties of superconductors. In particular, Abrikosov showed that Ginzburg-Landau theory predicts the division of superconductors into the two categories now referred to as type I and type II. Abrikosov and Ginzburg were awarded the 2003 Nobel Prize for their work. Landau had received the 1962 Nobel Prize for other work, and died in 1968. The four-dimensional extension of the Ginzburg-Landau theory, the Coleman-Weinberg model, is important in quantum field theory and cosmology. Also in 1950, Maxwell and Reynolds et al. Found that the critical temperature of a superconductor depends on the isotopic mass of the constituent element. 36-37 This important discovery pointed to the electron-phonon interaction as the microscopic mechanism responsible for superconductivity. The complete microscopic theory of superconductivity was finally proposed in 1957 by Bardeen, Cooper, and Schrieffer. 34 This BCS theory explained the superconducting current as a superfluid of Cooper pairs of electrons interacting through the exchange of phonons. For this work, the authors were awarded the Nobel Prize in 1972. The BCS theory was set on a firmer footing in 1958, when N. Bogolyubov showed that the BCS wave function, which had originally been derived from a variational argument, could be obtained using a canonical transformation of the electronic Hamiltonian. 38 In 1959, Lev Gorkov showed that the BCS theory reduced to the Ginzburg-Landau theory close to the critical temperature. 39-40 Generalizations of BCS theory for conventional superconductors form the basis for the understanding of the phenomenon of superfluidity. because they fall into the lambda transition universality class. The extent to which such generalizations can be applied to unconventional superconductors is still controversial. Further history: the first practical application of superconductivity was developed in 1954 with Dudley Allen Buck's invention of the cryotron 41. Two superconductors with greatly different values of the critical magnetic field are combined to produce a fast, simple switch for computer elements. Soon after discovering superconductivity in 1911, Kamerlingh Onnes attempted to make an electromagnet with superconducting windings but found that relatively low magnetic fields destroyed superconductivity in the materials he investigated. Much later, in 1955, G.B. Intima 42 succeeded in constructing a small 0.7 Tesla iron core electromagnet with superconducting niobium wire windings. Then, in 1961, J. E. Kunzler, E. Buehler, FSLHSU, and J. H. Wernick 43 made the startling discovery that, at 4.2 Kelvin, niobium, tin, a compound consisting of 3 parts niobium and 1 part tin, was capable of supporting a current density of more than 100,000 amperes per square centimeter in a magnetic field of 8.8 Tesla. Despite being brittle and difficult to fabricate, niobium, tin has since proved extremely useful in supermagnets generating magnetic fields as high as 20 Tesla. In 1962, T.G. Berlincourt and R.R. Hake 4445 discovered that more ductile alloys of niobium and titanium are suitable for applications up to 10 Tesla. Promptly thereafter, commercial production of niobium, titanium supermagnet wire commenced at Westinghouse Electric Corporation and at Huachang Corporation. Although niobium, titanium boasts less impressive superconducting properties than those of niobium, tin, niobium, titanium has, nevertheless, become the most widely used workhorse supermagnet material, in large measure a consequence of its very high ductility and ease of fabrication. However, both niobium, tin and niobium, titanium find wide application in MRI medical imagers, bending and focusing magnets for enormous high-energy particle accelerators, and a host of other applications. Connectus, a European superconductivity consortium, estimated that in 2014, global economic activity for which superconductivity was indispensable amounted to about €5 billion, with MRI systems accounting for about 80% of that total. In 1962, Josephson made the important theoretical prediction that a supercurrent can flow between two pieces of superconductors separated by a thin layer of insulator 46. This phenomenon, now called the Josephson effect, is exploited by superconducting devices such as SQUIDs. It is used in the most accurate available measurements of the magnetic flux quantum phi 0 equals h/2e, where h is the Planck constant. Coupled with the quantum Hall resistivity, this leads to a precise measurement of the Planck constant. Josephson was awarded the Nobel Prize for this work in 1973-47. In 2008, it was proposed that the same mechanism that produces superconductivity could produce a superinsulator state in some materials, with almost infinite electrical resistance. 48. The first development and study of superconducting Bose-Einstein condensate, BEC, in 2020 suggests that there is a smooth transition between BEC and Bardeen-Cooper-Schrieffer regimes. 4950 High temperature superconductivity. Main article, High temperature superconductivity timeline of superconducting materials. Colors represent different classes of materials: BCS, dark green circle, heavy fermions based, light green star, cuprate, blue diamond, Buckminster fullerene based, purple inverted triangle, carbon allotrope, red triangle, iron pnictogen based, orange square, strontium_ruthenate, gray pentagon, nickel based, pink 6-point star. Until 1986, physicists had believed that BCS theory forbade superconductivity at temperatures above about 30 K. In that year, Bednorz and Muller discovered superconductivity in lanthanum barium copper oxide, LBCO, a lanthanum-based cuprate perovskite material, which had a transition temperature of 35 K, Nobel Prize in Physics. 1987, 7. It was soon found that replacing the lanthanum with yttrium, i.e., making YbCO, raised the critical temperature above 90 K. 51. This temperature jump is of particular engineering significance, since it allows liquid nitrogen as a refrigerant, replacing liquid helium. 51. Liquid nitrogen can be produced relatively cheaply, even on-site. The higher temperatures additionally help to avoid some of the problems that arise at liquid helium temperatures, such as the formation of plugs of frozen air that can block cryogenic lines and cause unanticipated and potentially hazardous pressure buildup. 52-53. Many other cuprate superconductors have since been discovered, and the theory of superconductivity in these materials is one of the major outstanding challenges of theoretical condensed matter physics. 54-55. There are currently two main hypotheses: the resonating valence bond theory and spin fluctuation, which has the most support in the research community. 56. The second hypothesis proposed that electron pairing in high-temperature superconductors is mediated by short-range spin waves known as pyramagnons. 57-58. Dubious, discuss in 2008, holographic superconductivity, which uses holographic duality or AD/CFT correspondence theory, was proposed by Gubser, Hartnoll, Herzog, and Horowitz, as a possible explanation of high-temperature superconductivity in certain materials. 59. From about 1993, the highest temperature superconductor known was a ceramic material consisting of mercury, barium, calcium, copper, and oxygen, HgBa2Ca2Cu3O8 plus delta, with Tc equals 133 to 138 K. 60-61. In February 2008, an iron-based family of high-temperature superconductors was discovered. 62-63. Hideo Hosono, of the Tokyo Institute of Technology, and colleagues found lanthanum oxygen fluorine iron arsenide, Lao1XFX-Faz, an oxypnictide that superconducts below 26 K. Replacing the lanthanum in Lao1XFX-Faz with samarium leads to superconductors that work at 55 K. 64. In 2014 and 2015, hydrogen sulfide, H2s, at extremely high pressures, around 150 gigapascals, was first predicted and then confirmed to be a high-temperature superconductor with a transition temperature of 80 K. 65, 66, 67. Additionally, in 2019 it was discovered that lanthanum hydride, La10, becomes a superconductor at 250 K under a pressure of 170 gigapascals. 68-67. In 2018, a research team from the Department of Physics, Massachusetts Institute of Technology, discovered superconductivity in bilayer graphene with one layer twisted at an angle of approximately 1.1 degrees with cooling and applying a small electric charge. Even if the experiments were not carried out in a high-temperature environment, the results are correlated less to classical but high-temperature superconductors, given that no foreign atoms need to be introduced. 69. The superconductivity effect came about as a result of electrons twisted into a vortex between the graphene layers, called skyrmions. These act as a single particle and can pair up across the graphene's layers, leading to the basic conditions required for superconductivity. 70. In 2020, a room temperature superconductor, critical temperature 288 K, made from hydrogen, carbon, and sulfur under pressures of around 270 gigapascals was described in a paper in Nature. 71-72. However, in 2022 the article was retracted by the editors because the validity of background subtraction procedures had been called into question. All 9 authors maintain that the raw data strongly support the main claims of the paper. 73. Applications. Main article, Technological Applications of Superconductivity. 010. Video of superconducting levitation of YbCO. Superconducting magnets are some of the most powerful electromagnets known. They are used in MRI/NMR machines, mass spectrometers, the beam steering magnets used in particle accelerators, and plasma confining magnets in some tokamaks. They can also be used for magnetic separation, where weakly magnetic particles are extracted from a background of less or non-magnetic particles, as in the pigment industries. They can also be used in large wind turbines to overcome the restrictions imposed by high electrical currents, with an industrial-grade 3.6 MW superconducting windmill generator having been tested successfully in Denmark 74 in the 1950s and 1960s. Superconductors were used to build experimental digital computers using cryotron switches 75 more recently. Superconductors have been used to make digital circuits based on rapid single-flux quantum technology and RF and microwave filters. For mobile phone base stations, superconductors are used to build Josephson junctions, which are the building blocks of SQUIDs, superconducting quantum interference devices, the most sensitive magnetometers known. SQUIDs are used in scanning squid microscopes and magnetoencephalography. Series of Josephson devices are used to realize the SI volt. Superconducting photon detectors 76 can be realized in a variety of device configurations. Depending on the particular mode of operation, a superconductor, insulator, superconductor Josephson junction can be used as a photon detector or as a mixer. The large resistance change at the transition from the normal to the superconducting state is used to build thermometers in cryogenic microcalorimeter photon detectors. The same effect is used in ultrasensitive bolometers made from superconducting materials. Superconducting nanowire single photon detectors offer high speed, low noise single photon detection and have been employed widely in advanced photon counting applications. 77 other early markets are arising where the relative efficiency, size, and weight advantages of devices based on high temperature superconductivity outweigh the additional costs involved. For example, in wind turbines, the lower weight and volume of superconducting generators could lead to savings in construction and tower costs, offsetting the higher costs for the generator and lowering the total levelized cost of electricity, LCOE. 78 promising future applications include high-performance smart grid, electric power transmission, transformers, power storage devices, compact fusion power devices, electric motors, e.g. for vehicle propulsion, as in VAC trains or maglev trains. Magnetic levitation devices, fault current limiters, enhancing spintronic devices with superconducting materials 79 and superconducting magnetic refrigeration. However, superconductivity is sensitive to moving magnetic fields, so applications that use alternating current, e.g. transformers, will be more difficult to develop than those that rely upon direct current. Compared to traditional power lines, superconducting transmission lines are more efficient and require only a fraction of the space, which would not only lead to a better environmental performance but could also improve public acceptance for expansion of the electric grid. 80 Another attractive industrial aspect is the ability for high power transmission at lower voltages. 81 Advancements in the efficiency of cooling systems and use of cheap coolants such as liquid nitrogen have also significantly decreased cooling costs needed for superconductivity. Nobel Prizes for Superconductivity. Heike Kamerlingh Onnes, 1913. For his investigations on the properties of matter at low temperatures which led, inter alia, to the production of liquid helium. John Bardeen, Leon N. Cooper, and J. Robert Schrieffer, 1972, for their jointly developed theory of superconductivity, usually called the BCS theory. Leo Essegy, Ivor Yaber, and Brian D. Josephson, 1973, for their experimental discoveries regarding tunneling phenomena in semiconductors and superconductors, respectively, and for his theoretical predictions of the properties of a supercurrent through a tunnel barrier, in particular those phenomena which are generally known as the Josephson effects. George Bednorz and K. Alex Muller, 1987, for their important breakthrough in the discovery of superconductivity in ceramic materials. Alexey A. Abrikosov, Vitaly L. Ginzburg, and Anthony J. Leggett, 2003, for pioneering contributions to the theory of superconductors and superfluids. 82.